So hello everyone, welcome back to another class of Stereochemistry, and in this particular class we are talking about the concept of chirality. So if you have directly come to this particular video, then I will suggest to please watch the previous videos for a better understanding, and if you are on revision, then you can stay in this particular video. So before entering the chirality, let us talk about what is the chiral and chirality. So chiral, the word, is a Greek word that means handless or property of hand. Uh, now we'll discuss later that why it is called a properties of hand, but before that I want to emphasize you about the thing of optical isomers. See, it is clearly written here that if any isomers or any organic compounds are capable to rotate plane polarized light, then it is called rotate to plane polarized light either clockwise or anti-clockwise, then it is known as optical isomers. Now what is plane polarized light? We know that light is nothing but electromagnetic radiation. When light passes through a slit, then they will be a plane polarized. Okay, so now what happened that in the plane polarized light vicinity, if any organic molecule is there which are capable to deflect the plane polarized light either clockwise direction or anti-clockwise direction, then we can tell that the particular compound is a optical isomers. And a chiral molecule is usually must be able to rotate plane polarized light either clockwise or anti-clockwise direction. That doesn't matter right now. Okay, now what is the chiral molecule as in terms of symmetry property? Like it is clearly written that if any molecule doesn't have any element of symmetry, that means asymmetric molecules are usually considered as chiral molecule. Now why it is usually? Because there are certain characteristic should be there to be a chiral molecule. One of this, the chiral molecule must be able to rotate plane polarized light. Okay, now not only all the asymmetric molecules are usually considered as chiral, there was certain dissymmetric molecules also there. They are also shown the chirality. So we will discuss about what is the necessary condition of chirality at the end of this part. Okay, and the property of being chiral is known as chirality. As simple as that. Okay, so now let's talk about the broader definition of the particular things like chirality. Chirality is a property of a molecule that makes it non-superimposable on its mirror image. Okay, so let us understand this particular thing. Like example, this is my hand. If I put a mirror here, so the mirror image of this particular hand should be this hand. So these are the mirror image. Imagine there is a mirror. Okay, now if we directly put this particular hand to in my hand, so what happened that these two hands are not superimposable. If it is combined like this, then we can say this is a superimposable, but we are directly took this particular hand and put here, so it makes it a non-superimposable picture. That means it is a chiral. Our hand is a chiral molecule, and that's why it is written there. The chiral comes from the Greek word that is a property of hand. So our hand is chiral. Similarly, it is drawn here. Like in this particular picture, you can see what I am actually discussing about. That this is a hand mirror image is there. Now if we directly put this particular thing toward here, so it will not be superimposed. That means our hand is chiral. Similarly, this particular compound where it is clearly visible, that is the asymmetric molecule. So this particular also provide a non-superimposable mirror image. That means this molecule is also chiral. Okay, and what is chiral center? Chiral center, an atom, usually carbon, that has 4 different groups attached to it. Here is the carbon that contains 4 different groups leading to chirality of molecule. There is a chiral center. So here the chiral center is this particular carbon center is the chiral center. Now you may be wondering that why mostly carbon dominated chiral center we have observed. Here also written that usually carbon. Okay, so why only carbon is the key candidate for here to become a chiral center? Actually, mostly carbon is the carbon is the mainly widely used as a chiral center because there are certain reason is there. But however, the carbon is not only the candidate for the chiral center. Like here it is clearly written that carbon is not only the element that can exhibit chirality, other elements can also form chiral center under certain conditions. However, carbon is the most commonly discussed in organic chemistry for several reasons. First of all, it is a catenation property. Like we know that carbon-carbon bond formation quite easy, and it will form a long chain hydrocarbon. So if we just substitute the group, then it is a possibility of making a chiral center. Okay, and also it is usually forming a covalent tetrahedral bond, with sp3 hybridization. That means it can be stable in the sp3 and 4 carbon, or should be different condition that can be. And also due to the moderate electronegativity of the carbon bond, so what happens, the covalency gets increased. Okay, but however, not only the carbon, there was chirality observed with the non-carbon atoms like chiral silanes. Like silane containing 4 different particular group will be shown the chirality. Similarly, the chiral phosphines, there are the compounds, just phosphine oxides with 3 different organic group bonded to phosphorus will also show chirality. Chiral sulfoxides, compound like methyl phenyl sulfoxide, where the sulfur is bonded to a methyl group, phenyl group also shows chirality. Now here is the interesting thing. Although nitrogen can exhibit chirality in amines, but the rapid interconversion of the lone pair at room temperature usually prevent the isolation of enantiomers. So what happened to this particular nitrogen? Ideally, if we speaking that if the nitrogen contains 3 different R group, then it must be a chiral molecule. But what happened that if the R groups are small enough, then this nitrogen can undergo a ring flipping. Why the ring flipping happening? Because this particular isomers and this particular isomers having a very smaller energy difference, which can be achievable in room temperature, so, when the R group is small enough. So what happens, this particular will go rapid interconversion. So this particular one of the isomers has been not isolated properly, and that's why it will be shown as a achiral molecule. However, if the R groups are big enough to increase the energy difference between these two isomers, or the interconversion part or ring flipping part, not the ring flipping, it is the inversion part. So we can isolate this particular group or this particular amine, or we can say the chiral amine. Okay, so the pyramidal inversion highly depending upon the nature of R group. If the R group is big enough, then the pyramidal inversion will less likely to occur, and when the R group is small enough, then it will be more likely to occur. And when R group is big, then R group is big enough, like phenyl and some kind of bulky groups, then what happens that this particular amine become a chiral amine if the R's are different, or if there is a smaller group like methyl or ethyl, then it will show an achirality because of the lone pair rapid interconversion of the lone pair. Okay, or the pyramidal inversion we can say. Okay, now there are some unusual chiral molecules here. Usually quaternary amines are shown chirality because there is no chance of flipping or pyramidal inversion here. Okay, and the silylated, sulfonate and all kind of thing, and also the bridgehead nitrogen, which have no option to do a pyramidal inversion, so it will be a chiral molecule. Similarly, the carbenes also exhibits chirality in such cases, but they are actually less known and less important, but they are also shown chirality. Okay, now there should be an essential criteria for a molecule to be chiral, because we have seen that there is a very catches there, like this molecule is chiral, this was not chiral. So there is a tabulated form, or there are certain rules to be maintained by a molecule to become a chiral. First of all, that molecule should be asymmetric in nature. However, there are some disymmetric molecules also there, they are also show chirality. So it will be a not necessary condition, but it is a condition. Second one is the carbon group should have 4 different group. This is also not necessary because we can see the carbon, there is a 3 different group also there, but still it is a chiral molecule. Okay. Third is the molecule shouldn't have a plane of symmetry. This is a very important. If a molecule contain any kind of plane of symmetry, then the molecule become a chiral. And this is the property that molecule should be able to rotate plane polarized light. Okay. Now here in this particular example, you can see that this particular compound having a C2 symmetry, but still it is a chiral. That means the symmetric molecule is also chiral. Okay. And here in this molecule it is the mesotartaric acid. So here you can see there is a plane present here which makes this particular molecule a chiral because it have a plane of symmetry. Okay. So now let us talk about a little bit of definition of certain things that associated with the chirality. First is the homochiral. Homochiral system suggests a system or mixture where all molecules have same chirality. So basically what happens that if we take a molecules or a mixture of molecules when all the molecules are either R, all either R or all either S, then this particular compound is become homochiral. Now R is, it is a nomenclature of the chiral compounds, and we'll discuss in our future classes that how can we naming of or name the chiral centers and the organic compounds. Okay, then there is another thing, there is the prochiral. Prochiral is something, it is an achiral molecule, but it can be chiral through a single substitution or alteration. Like example, this particular compound. So here you can find that this particular carbon center have 3 different groups, 2 hydrogen is there, but somehow if we chemically clip this particular bond and then we replace this hydrogen with some kind of other group or other substitution, then what happens, this particular carbon center now become 4 different substituent, and now it can or also it will be a asymmetric molecule, and now it can be shown as a chiral molecules. So this type of molecule which contains 2 different hydrogens, okay, and if there is a possibility of interconversion, chemical interconversion to form 4 different groups or incorporating another group by changing this particular group, then it is called a prochiral center. And heterochiral center what suggests the exact opposite of homochiral. Like if any system or mixture containing molecule of different chirality RS, SR, and a mixture of proportion of R and S, then it will be called as a heterochiral mixture or heterochiral system. Example, racemic mixture. Now racemic mixture is something that in the particular mixture there is the 2 different isomers present in different portion. Like in racemic mixture there are 50-50 portion is there, R 50% R and 50% S was there. So this particular system we can consider as a heterochiral system. Okay, now we are talking about some different definitions. Like first is the epimer. Epimer is nothing but a type of stereoisomer where multiple chiral centers are present, but the 2 different isomers, 2 different stereoisomers are only differ in the configuration about 1 specific carbon atom. Example here, see this particular D-glucose and D-galactose. Here all the groups looking like same, but this particular OH are above, whereas this particular OH are below. However, you will find that why it is above, why it is below, because till now we are not learn about the representation. Just you can understand that this particular group is changed, and due to the change of this particular group orientation, the chirality change only this position. Now if you find little bit of fishy and little bit of confusing here, then I can tell you that hold on this particular part right now when we will discuss about the representation and as well as how to determine the chirality RS nomenclature, then you can come back and understand this particular thing. Just for the time being, just go through the definition. Okay. Now there is another important thing, that is the stereogenic center. Stereogenic center of an atom where the interchange of any two atom substituent results in a new stereoisomer. Example, like here in this particular chiral center, if we change the position of methyl and this OH group, then you can find that the chirality of this particular group has changed, like R to S, and that can be observed in the plane polarized light also, like if it is earlier goes for a clockwise direction deflection, now it will show an anti-clockwise direction deflection of the plane polarized light. So it can be shown that it is a chiral molecule, as well as this center is a stereogenic center. Chiral center as well as stereogenic center. Like changing this particular group will alter their absolute configuration, that is R2S or S2R or whatever it is. Now here, if we change this methyl and the hydrogen group, so it is also change relative configurations, like say the trans. Now changing this particular, it will become a cis. Now here also that the new stereoisomer has been formed. This is true. However, this particular is in the plane of symmetry. Now, as we know that if the molecule contain a plane of symmetry, then it will not become a chiral molecule. So this particular center is a stereogenic center, but not a chiral center. So from there we can come to the conclusion that all chiral center are stereogenic center, but all the stereogenic center are not chiral. This is a very important observation, as well as the conclusion you can say. Like all chiral center, if there is a chiral center, there should be a stereogenic center, but all stereogenic centers are not chiral center. Okay, so with this we have to end this particular class. So we have just quickly summarized what we learned. First, we have learned the chirality and the chiral centers, and also we have learned about the superimposable mirror image. Just trying to go there little bit. So we are talking about the chiral is a Greek word, that is mean the property of hands, and there is talking about the optical isomers, that whenever the organic molecule is able to rotate plane polarized light either clockwise or anticlockwise, then look at the optical isomers. And also if the molecule doesn't have a element of symmetry, or asymmetric molecule usually shows chirality. However, certain disymmetric molecules in the certain conditions will show the chirality, and the property of being chiral is known as chirality. We're also talking about definitions and also giving examples. Now, not only the carbon is a good candidate about the chirality, shown the chiral center, there is a different centers also there who can shows the chirality, like silanes, phosphines, sulfurides and all. And nitrogen case, if the R group is, amine case, is the R group is the big enough or bulky enough to diminish this pyramidal inversion, then it can be chiral, otherwise it is a chiral molecule. Then they're talking about some unusual chiral molecules. Then there is an essential criteria. The molecule should be asymmetric in nature, but it is not always true. Some disymmetric molecule also shows chirality. Also, the carbon molecule should have 4 different groups. This is also not necessary. Molecule should have plane of symmetry. This is very important. And molecule should be able to rotate plane polarized light. Then we are talking about the homochiral, prochiral and heterochiral center. The definition is here written. Then talking about the epimer and stereogenic center, and we came into a very interesting conclusion that all chiral center are stereogenic center, but all stereogenic center are not chiral. And with this we have end this particular lecture. If you have any doubt, there you can comment. And in the next lecture we are talking about enantiomers and diastereomer. So thank you for this particular lecture.